After successful application at the tire level, we further split up the receiving structure into suspension, bush, and body. All subsystems were experimentally characterized to enable developer to construct a virtual vehicle with hybrid models. We adopted dual approaches for suspension model. I will explain the FBS decoupling approach in detail a moment later. Afterward, we applied various technology to another type of suspension jig, so-called chassis module tester. The goal was to build credible simulation model for this tester. At first, we used experimental bush model to update the suspension model, and we used experimental jig model to relieve the effort of modeling jig with air bellows and sands, which are known as difficult to get credible model. Let's move on to the challenges of measuring the suspension strength function model adequate for FBS. This is due to the particularly difficult nature of the suspension. It cannot be characterized separately because they are attached to a wheel on one side and the body on the other. This makes it challenging to replicate the operational boundary conditions during component-only characterization, including preload due to the vehicle weight and the slip during drive. We already knew if the suspension is not modeled correctly, the results will not be accurate. Applying the FBS decoupling method successfully, we were able to create an accurate model with the frequency range required for road noise application. Next, we started to construct a test setup for FBS decoupling. At first, the jig was designed and validated using a simulation model to limit strong dynamic behavior or excessive stiffness so it could be coupled with the suspension. Then the suspension was coupled with the test jig and placed on the four-poster to make the suspension slip. From the test campaign, the required FRFs were measured. We measured approximately more than 30,000 FRFs. As the suspension system contained a large number of connection points, we applied extended FBS decoupling approach to ensure a more accurate model, which used additional information, so-called indicators, with the information at the coupling points. We developed two approaches for the better possible models. One way is we adopted an optimization scheme for the selection of indicators. In another way, we applied a singular value compensation method for pseudometrics inversion calculation. Our effort was successful. We could construct an accurate suspension model with dynamic behavior in each operational boundary condition.
Let's move on to the Bush transfer function model. There have been so many kinds of research on measuring bush characteristics experimentally. The FBS decoupling with receptance model and VPT gave us additional two options for bush models as presented in the paper. Despite the limit of not being able to apply large displacement or preload, this approach gave us attractive advantages such as higher frequency range coverage and 6 DOF data, which is adequate for road noise and PMVH application.
In detail, we made an assembled model with bush and jig experimentally and simulation model for jig. And we calculated the bush strength function model by FBS decoupling. Then we compared this method with other methods used before. It showed good accuracy with reasonable measuring efforts. There is no reason why we cannot use the experimental bush model for road noise and PMVH development rather than the simulation Bush model. What is your idea?
As you know, the credibility of a vehicle model depends on the integrity of the system or subsystem models. This is an example of how much a Bush model can influence the suspension model. Afterward, we plan to make P-mount Bush model database to expand up to a higher frequency range. Let's move on to the chassis module MVH tester. The goal was to build a credible simulation model for the chassis module tester, where force sensors are installed at the input and output. From the conventional interface force approach, we needed every model input and output jig with air bellows and sand, which took a lot of work to get a credible simulation model.
To solve this problem, we authored a test model for the input module, as we did for the tire system. By using the test model of the source and simulation model of the receiver, the interface force at the wheel center was calculated according to hybrid component-based DPA, without the effort of modeling jig system. And it is shown the output force estimated from the input test model showed a better correlation than jig FE modeling. To reduce remaining error, it is necessary to get a credible output jig model, which was very difficult. Instead of using interface force at the force sensor, a blocked force model at the center of mount bush was used to remove the modeling effort for the output jig. Plus, blocked force at the input and output could show the suspension's representative force isolation property independent of jig. Additionally, we have the plan to use suspension's blocked force for evaluating vehicles' road noise by simulating real-road driving with a dedicated exciter.
Let's move on to the body system. Fortunately, there is no particular operational boundary condition. Only a free condition at the connection needs to be applied. We compare the FRFs measured from various methods, such as newly adopted VPT estimation at the center point and conventional measurements at adjacent points. There was a significant difference between measurements. However, surprisingly, we have discovered a good correlation between the test and simulation model at the center point. The test body model was processed into a standard format and stored in the model database for road noise estimation. Up to now, I have explained how to author tires, suspension, bush, and body models experimentally. However, I admit that the process for measuring experimental model is somewhat complicated. So, there was a study on how to author the model efficiently by using test and simulation technology, so-called SEMM. The concept of this technology is replacing the part of simulation with test model based on FPS coupling and decoupling approach. The advantage of this approach is that we can control the amount of test campaigns. There are 4 variations in SEMM based on the method of expansion from simulation to actual test while making the simulation model. Let me introduce an example of an extended compatibility equation. We selected a simple structure for case study. We authored a test model for SEMM with much less effort than for FBS. Then I authored a simulation model with extended points, including a target and additional response indicator. Then we compared the target result from simulation, test, and SEMM. We can clearly see that the SEMM result showed a good correlation with the test. This technology can be used to update the simulation model credibly with minimum effort by replacing the conventional FE model correlation.